And without further ado, I'd like to present the session here. So the session, despite the slight change on the slide there, is probabilistic spying on encrypted tunnels. Brendan Nimchek and Prasad Rao. So take the floor, guys.
Thanks, Brian. So thank you for coming. We appreciate it. We want to talk about a tool release we're doing called Pacumen, which is used for identifying what encrypted tunnels are what application protocols are being used over them. In some cases, you can even identify what websites are being visited over them. And we put it in a generic way so that everybody could use it and train it for their own applications that they want to identify, and over whatever type of VPN they'd like. So we're going to use SSH as an example today, but it is not specific to SSH. My name is Brandon Nimchek, as he mentioned, and this is Prasad Rao. So I already kind of mentioned what Pacumen is, but essentially Pacumen is a tool that has two different steps. You can collect a bunch of data that you know is of a certain type of encrypted tunnel, and you know that a certain application is being used over it. And then you can train Pacumen to recognize encrypted tunnels that are also using that application. So for instance, you can, and what we're going to use as an example today, is detecting if somebody is utilizing Skype over an SSH tunnel. It is very accurate with Skype. Not all applications are quite as accurate, but it is very application dependent. So with that, I'm going to turn it over to Prasad because this has been built on over a very long time. This is not all entirely original. We do have a lot of original stuff in here, but we are, of course, standing on a lot of prior research that came out of academia.
Thank you, Brandon. We totally believe in standing over the shoulders of giants, and this is a sampling of what the giants have done over 14 years or more. The first line, the authors showed the world how to compare different machine learning algorithms, not just by the quality of the results, but also by things like how much time the algorithms took, how much memory it took, and so on and so forth. They used 33 different machine learning algorithms on 32 different sets of data, but the data was totally unrelated to what we are doing here. In the next line, McGregor and his co-authors used expectation maximization algorithm, which is an unsupervised learning algorithm, which means that the data doesn't have labels on it, to classify and cluster traffic flows, and they used Kvyat diagrams to visualize the clusters. What they found was that the clusters that they find naturally correspond to the applications which use the tunnels, which created the traffic. The next line consists of a work which used the similar technique for doing application identification over traffic for the purposes of traffic shaping and assuring QoS. All the remaining lines, I'm not going to go line by line, but please memorize this chart because there's going to be a test. All the remaining lines correspond to a work that people try to identify stuff over tunnels. The first one, if you notice, at least one co-author has an unpronounceable name, and we have kept up with the tradition. Yeah, Karagiannis et al. Used a technique that used a lot of information. They built a graph. They knew who the clients were, who the servers were, what the social function of the clients and servers were, and they used graph clustering to identify applications. But their technique could not be used to identify applications from a single link. that's what the later rows do. Basically, what's happening in the later rows is that they use different machine learning techniques, supervised techniques such as decision trees, which is some kind of a sophisticated 20-question game, or a statistical technique such as naive Bayes, or they use clustering such as k-means or nearest neighbors. What the remaining rows do is apply a bunch of promising machine learning algorithms on their data and come up with the performance that is shown in column 3. But bear in mind that each line represents years of work done by a sizable team of graduate students. Some of them had awesome results. For instance, the Bernal work requires only 5 packets to identify one particular application. Some of the other ones were similarly restrictive in the sense that they can just identify Skype or they can just identify SSH and so on. But the main point I want to leave you with is that these different techniques, they come with a significant barrier to entry. That is, you must recreate their tool set, you must recreate their data collection apparatus, and so on and so forth. And what my co-author and I have tried to do is to lower the cost, lower the barrier to entry to this kind of research. At this point, I'll turn it back to Brandon.
So as Prasad was mentioning, there's been a lot of work. No code has been released that we can find from academia on any of this. There's a lot of results-only papers, and some of the results are difficult to interpret because there's a lot of data pre-processing that happens beforehand, and if you don't do things exactly like they did, you get completely different results. So we wanted to make an open source framework that makes it nice and easy for anybody to try this. Other issues with the previous work is pretty much all of them focus on one application at a time. Our tool is meant to work on pretty much almost any type of encrypted tunnel, and it will work with pretty much any application. When I say application, I want to be clear, I don't just mean a standalone application as Skype, but for instance, this also works fairly well for identifying that somebody is visiting Facebook using Chrome, or somebody is using, actually no, Twitter fails for several reasons, but there are many websites, very popular websites, that you can also identify that they're visiting them, even though you have no idea, you can't see any of the IP, you know, because it's just random noise, theoretically. So how does it work? You don't have to write any custom code if you want to start identifying an application. We've tried to take a code writing problem and turn it into a data collection problem, which comes with its own sets, but you can, it's pretty easy to collect this data because you simply run Wireshark, do it, let it run for 20 hours, and then you're done. So the typical workflow is you collect some example data, like I said, just run in Wireshark, but you have to know what the tunnel is being used for. When you do this, when you collect the data, it's best to only collect one application over that tunnel, but it will still be able to detect the application if in the real world many applications are being used over the tunnel, and we'll talk a little bit about why that is. You then run a training script, and Pachyman then outputs a classifying file. You then get some new data that you don't know anything about, and you can run it through the classifier, and it will tell you what applications it knows about that are in there. And it'll give you a confidence, a probability that that application is being used. So if it says it's 99% sure, then you're pretty likely. If it says 0.6, you know, chances are it may not be true. And you just repeat. So we don't have enough time to go into a huge amount of detail internally how it works, but what it does is it looks at packet sizes in 10-second windows, what packet sizes show up, and with that it will replicate, or it will update its confidence that an application is being used. So, and then it just repeats every 10 seconds. So, quick little animation, you know. We're looking at 10 seconds of data, we see 2 packets of size A, 1 packet of size B, 3 packets of sizes that Pachyman did not decide mattered during training. And the reason it's important that we throw away many packet sizes that don't matter is because that's how we allow this to identify particular applications when they're used amongst many other. I don't know about you guys, I use SSH tunnels for everything, especially if I'm at Black Hat. I don't trust the network here, sorry. And you know, I'll have email, all kinds of stuff running in there. Yet, I still want to be able to identify if I'm using one particular application. Takes these sizes and it feeds them into the classifier. And then it updates its confidence that that particular network flow does in fact contain the application that you care about. So we actually have built in a couple different classifiers. The decision trees work best. The reason the decision trees work the best is because they allow a particular type of relationship to be looked for. In particular, it allows you to say, okay, well, I see packet size X. That means I should also see packet size Y 4 times. Additionally, we have another type of classifier called mixed Gaussian likelihood functions, which is still in there because we wrote it to try it out. To be honest, it doesn't work as well with decision trees, so I would stick to those for now. We will add more, and one of the things that Prasad did an awesome work with was going through and taking all the different machine learning algorithms in Weka and trying the same thing, and we've got a script where you can export this to run it through pretty much any standard machine learning stuff to take our features. The decision trees we're using were fairly heavily modified. They're not a standard algorithm to build them, but we had to do that because it works quite well in general, better than the kind of standard machine learning algorithms because it takes into account some specific problems that come up. So just a really quick review. I think everyone in here probably knows what a decision tree looks like, but in case you don't, it looks like that. Mixed Gaussians are a little bit different. In this, you assume that your data comes from a Gaussian distribution. In 2 dimensions, that looks like a disk on the left-hand side. A mixed Gaussian is simply one that has been a disk that has been rotated, stretched, rotated some more, and so on. If you assume your data comes from some mixed Gaussian, you can use this nifty little equation down at the bottom, which we don't really have time to dive into, but if you Wikipedia it, you can find it. It's called the likelihood. So let's just do a demo. Okay, so we don't have any classifiers at this point, but we've collected a whole bunch of data that we know is Skype over SSH, because we know it when we collected it. We also collected a bunch of data that we know is not. So we go ahead and we're going to train it for Skype, ssh.skype. And it goes through, and it's actually a pretty quick training process. As you can see, it's done already. And it just read in all the PCAPs, turned them into feature vectors, and then it built the classifier, and you can see that we now have a classifier. So we also have some data that we did not use for training, which we've got in this directory right here. And you know, we've got a bunch of Chrome, Gmail, a bunch of Skype, some Firefox, you know, things like that thrown in. And so I want to go ahead and classify against all of those and see which ones contain Skype. We know the answer, but we just want to prove that the program works. It can take a minute because we have a lot of PCAPs there. It won't take too long though. All right, so on the left-hand side is the probability that Skype is being used over SSH in this particular network flow. You'll see that it's 99.999% sure that the top two PCAPs contain Skype, which is in fact true. On the other hand, you get into the like 35% range with LinkedIn. And the reason for that is LinkedIn has some common sizes that overlap, and so sometimes it'll look like Skype. But since it doesn't always look like Skype, it correctly does end up below 50%. And you see that you very quickly, in the vast majority of the data, end up at these 0.0001, and that's, you're never going to get a 0% chance because it's built in for numerical stability that you can never have a 0% chance. And you see it just goes on for all of the different PCAPs. And please keep in mind, none of these PCAPs were used in the training. So these are just entirely new PCAPs to the program. I'd like to point out that this will work for any tunnel type. You can just, all you have to do is Wireshark that tunnel type. We're using SSH as an example because I like SSH. You could use OpenVPN, you could use whatever. As far as defending against this, the simplest way to defend would be for a tunnel to pad all packets to the same size and to make sure that they go out at a set interval, say maybe every 10 milliseconds. 10 minutes? Okay. And in fact, I believe that is in the plans for SSH is to add a mode like that, but it doesn't currently exist. And it's because it's not really performant to do that. So I want to be clear, we're not breaking cryptography here at all. We make no attempt to decrypt anything. We're simply saying, well, you want to make your application performant on a network, and that means that you have to do certain things, like not send more data than you need to, more often than you need to, and that means that you're going to have a unique signature that we can pull out. And so that's it. I'd also like to thank my coworker, Vib. He worked really hard at helping us collect all this data. Are there any questions? Yes, could you come up and use the microphone so that people can hear you, please? Oh, by the way, that URL, it is up and live now. You can download it and use it yourselves.
So I'm wondering about, I find it strange that you had a hard time distinguishing between LinkedIn and Skype, because Skype, after all, is quality of service based, and the inter-arrival time of that should be very different from LinkedIn, which has got user interface. No?
So we didn't really have a hard time. I mean, it did still properly say there was a less than 50% chance. The point that I was trying to make is, it just so happens you're going to have a lot of conflicts between sizes. There's going to often be sizes that show up in multiple applications, not just because they might use that, but because encryption algorithms pad. So, you might have one, Skype uses 18 bytes and LinkedIn uses 20, but then they both show up as 32.
Right, but it's the timing is very, very distinct for Skype.
The timing, though, is implicit because we don't explicitly put timing into it.
You don't.
What we do is we look at what sizes show up in a set time window.
I see. Okay. All right.
So one thing I want to add is we can add extra features. So right now we are just Right now we are just using the packet sizes as the features, but we can add timing-based features. We can add many other features.
It's been used in Skype, for example,
We actually did mess around with that. There are some issues with it. It's very noisy because of network latency to add timing in explicitly, which is why we switched to an implicit thing where we just have a set size time window that we look at.
First of all, great talk. How much data did you use? I mean, it was fairly quick, both the training and the evaluation. So how much data was lying around there?
I will tell you exactly.
And while you're switching, how much would you, how much should we use to get a decent result?
The more the better. In some cases, as little as a couple hours is enough, but we found that at least 12 hours in most cases is the best. So if you if you just go ahead and start up your application, run over the tunnel and collect that data, and let it run for 12 hours, you'll be good in most cases. One point I should make is it's best if you let it idle. The reason for that is because that's where you're going to get the most consistent sizes that will show up all the time, and it makes the best signature.
Thanks.
Have you checked about resistancy against version changes on the client, like another version of Skype on the client, another platform used? Or is it just classifying your own traffic as you recorded it?
When the Skype version changes, what should we do? The answer is retrain.
The answer is you might have to create multiple classifiers.
Okay.
So you might have to create one for Skype version X and one for Skype version Y. But in many cases, if they don't change the internals of the application a lot, it'll still work.
Okay, thanks.
Are there any other questions? Well, thank you very much. I would love if you check out the code and send us some feedback.